All right, the next few things that we have in the notes are some definitions, some remarks that are a little bit more technical. It's good to read over them, but I will not read over them unless it's very, very, very important in the video. You can pause and you can read them for yourself. What we do talk about here is the continuity at a point. So this definition is very important. So a function is continuous at a point x equals c if the limit, so let's look at the left-hand side, the limit as x approaches c of f of x is equal to f of c. So there's a lot actually here to unpack. It's very simple to look at this one thing, but this is really saying two things, or excuse me, this is saying three things. Thing number one that it says is that the limit as x goes to c of f of x exists. Because how can you have something equal to something else if one of those two things doesn't exist? If it's equal to something that exists, then it has to exist. Yeah, sounds weird when you say it out loud, but I want to emphasize the limit exists. Second thing this says is that f of c is defined. Again, sort of with existence. If you're going to assign a value to something, you have to make sure that it is, present and exists. 3 is really that the value of the limit, so in other words, part 1 is the same as the value in part 2. So in other words, whatever f of c is. And we can go ahead and look at what happens if we break these assumptions. So let's go ahead and take a look at the first assumption. What would a graph look like where, let's break number 1. So what happens if the limit doesn't exist? If the limit doesn't exist, that means the left and the right hand approaches, the one-sided limits, they have to yield different answers. So a graph where number 1 is not satisfied, I'll draw this over here on the side. So if number 1 fails, then we get a graph that might look something like this. There we go. The left and right hand limits exist. Okay. Right? The right hand limit is this y value. The left hand limit is this value. So they exist. The one-sided limits always do. But in this case, they don't match, so the limit doesn't exist. So condition 1 fails. Condition 2 is satisfied, though, because if this value here, let's say that this is x equals c, clearly, if we plug in c, we get this y value. So it's defined. And number 3, we don't have to really worry about number 3. Technically, number 3 fails, because number 3 fails if either 1 or 2 fail. Because number 3 is comparing the value of two things, and if one of those two things doesn't exist, how can you compare the value? You can't. So what about condition number 2? What if number 2 fails? What does that look like? Well, if number 2 fails, that means that f of c is undefined. So you could have something like this. Here the limit exists, the left limit exists, the right hand limit exists, and they give the same y value, therefore the limit exists. But there's a little hole there. The function f is defined everywhere except at x equals c. We call that a hole discontinuity. The previous graph that we drew, where condition 1 failed, that is a jump discontinuity. This is sometimes called a hole or a removable discontinuity. Now, for each of these graphs, I made only 1 and 2 fail. What about, can 1 and 2 simultaneously fail? Yes. Functions can be failures in multiple dimensions. So here we have a hole and a jump, but instead of one of them being filled in, they're both empty. They're both open. So in this case, conditions 1 and 2 fail. Okay? Now, there is another thing here, which is number 3 failing. So let me move this, let's get rid of this for a second. Let's do number 3 fails. Number 3 fails, but 1, and 2 do not. So what's that look like? Well, for that, if 1 doesn't fail, that means the limit has to exist. So I get this. But right now with that hole at x equals c, condition 2 is not met. It's still failing. Well, we can go ahead and just put a solid circle somewhere so that at least f of c is defined. So there you have it.